Here in Chapter 6 we have two basic reactions. We have an sn2 versus an sn1 mechanism that we're going to talk about. And the sn2, or in both of them, they are both, the Sn stands for substitution nucleophilic. The difference between the two reactions is the sn2 is a bimolecular reaction, whereas the sn1 is a unimolecular reaction. And the difference in that is in the bimolecular reaction, in the rate determining step, the nucleophile has to form a bond to the carbon with the leaving group. So the nucleophile has to attack the carbon, kicking out the leaving group all in one step. So the nucleophile and the carbon with the leaving group have to come together in the rate determining step for it to be an sn2 mechanism. So there's one step to that mechanism, whereas in the sn1, the unimolecular reaction, the rate determining step is the loss of the leaving group to form the trigonal planar cation, and then the nucleophile adds to it to form your final product. So in these two reactions, we have to decide what type of starting material works best for each one. In the first one, we need to have no or very low steric interactions in the reaction. So in this one, we don't have much steric hindrance around because we only have the one methyl. So this would be best for an sn2, the primary leaving group, because the nucleophile can get in past all the hydrogens, which were much smaller than a bunch of methyl groups, to form the carbon, kicking out the leaving group. In the second example, we have a lot of steric interactions with the three methyls all around the carbon with the leaving group on it. So this one would be easiest for the leaving group to leave to form the planar cation. This is a tertiary compound, so the tertiary carbocation is most stable, so it's easiest to form. So this would work best for the sn1 mechanism because we can form the cation on the tertiary carbon. So here we have the mechanism and the reaction coordinate diagram for both reactions, the sn1 and the sn2. And in sn1, remember, we have to form the cation, have the leaving group leave to form the trigonal planar cation, and then our iodide adds to it to form our product. Now in the mechanism, make sure you put in the arrows between each step, and also the arrows needed for each step in the mechanism. So in this first reaction, we have our starting material, the alkyl chloride and the iodide, and the rate determining step is we have to get to the cation and the chloride and the iodide. And then it undergoes a much smaller reaction activation energy to get to the product where we have the alkyl iodide and the chloride around. So the first step of the mechanism is the hard one, where we have the activation energy we have to get over to get to the transition state, and then the second activation energy is much lower to get down to the products. Now in the transition state for these reactions, here we have the first transition state, and in this transition state all we have going on is the bond between the carbon of the T-butyl and the chlorine, in that bond breaking. So we have something like this for the transition state, where the carbon is forming a partial positive and the chlorine is forming a partial negative as that bond breaks between the carbon and the chlorine. Now, when we look at the second transition state, we will see the exact same thing, except for we're not breaking a bond to a chlorine, but we're forming a bond between an iodide and that carbon of the T-butyl group. So we have almost the exact same thing, just we have the iodide in place of the chloride that we had in the first one. So that's the reaction coordinate diagram for the first reaction, where we have to go via an sn1, where we form the trigonal planar cation, and going to the product having the iodide in place of the chloride. In the sn1, or any one mechanism, we have to form the cation. Okay, if we do not go through the intermediate with the cation, we have drawn the mechanism wrong and need to go back and try it again. In the second reaction down here, we have sn2, where we have a primary leaving group, and the iodide comes in, displaces the chloride, giving us that product. We only have one step to our mechanism, so we're only going to have one peak that we have to go over. We have the activation energy here. We have our starting material of the alkyl chloride going to the alkyl iodide. I got an extra carbon in that. And then here at the transition state, we have the iodide coming in and the chlorine leaving all in one step. So in this carbon, we have the chloride, we have the iodide. Remember, they both have a partial negative on them because the iodide is starting with a negative, the chlorine ends with a negative, and then the carbon has our 4 carbon chain off of it, 2, 3, 4, and then the 2 hydrogens, since it is a primary carbon. And the transition state for this is going to look something like this, where the iodide's coming in from the opposite side of the chlorine to form the bond in the transition state for the sn2 mechanism. And here we have the basic guidelines for trying to decide what will happen in a substitution reaction, or actually a substitution or an elimination reaction when we get into chapter 7. You'll see this a few times throughout this section. The strength of the base or nucleophile tells us what can happen in the reaction. You need to know this, how to decide between sn2, sn1, E2, and E1 mechanisms. Okay, this page is very important. Keep it handy as you're going through things. The strength of the base is the first thing we want to look at. If we have a strong base, strong nucleophile, it has to be a 2 mechanism. A weak base, weak nucleophile, it has to be a 1 mechanism. If we have a primary halide, it's going to be a 2, either a substitution or an elimination, depending on what kind of nucleophile we have. If we have a tertiary leaving group, if we have a strong base, it'll be an E2, otherwise it'll be an E1 or an SN1. And if we have heat, it'll be an E1 elimination. Okay, and the secondary halides can be any of the 4 mechanisms, depending on if we have a strong base, strong nucleophile, it'll go via the 2 mechanism. If we have a weak base, weak nucleophile, it'll go via 1 mechanism. And we have to keep track of what type of thing we have and know what everything is. So water, methanol are weak base, weak nucleophile. Hydroxide, methoxide are strong base, strong nucleophiles. If we have a polar protic solvent, it favors a 1 mechanism. If we have a polar aprotic solvent, it favors a 2 mechanism because they stabilize just the cation. And DMSO, DMF, HMPA, ether, and THF are excellent examples of polar aprotic solvents. High temperature favors elimination, so when you see the delta, that means we're heating the reaction, and that favors an elimination product. And some bases favor substitution. If they're small, like methoxide, hydroxide, they favor substitution, whereas something large like T-butoxide favors elimination. You have to know this page, keep it around, print it out from your PDF that you all have a link to, and keep it handy as you're working problems in the book, and make sure you look at what's going on and think about what this page tells you and how you go about using this to help you identify what can happen in the reactions. And be sure to come by or send me an email, and if you're having problems with anything, take a picture of it and send me an email with the picture.